Welcome everyone to the fourth video on machine learning and software engineering. In this part, we will continue to cover the machine learning pipeline of a project. So we started to cover last time what is the machine learning project lifecycle. We examined the business problem, the goal definition, and the data collection and preparation steps. Now that we have clean data, we want to make it usable by a machine learning model, and we want to train this model and to evaluate it. So we will cover these three steps in this video: feature engineering, model building, and model evaluation. Okay, now let's review the next step of the life cycle of a machine learning project. The next step is feature engineering. So in feature engineering, the goal is to transform our raw data into tidy data with numerical or categorical features. So here there are different points. The first is raw data. So raw data is the data that we have at the beginning. So if I take the example of a spam filter, what we have at the beginning is a formatted email with a topic, with a title, with a body that may be HTML, that can have some formatting, and we'll have a note or two, we have a from, a to, email address, we have a lot of different metadata, also things like that. So this is raw data. This is not directly usable for a machine learning model. So we have to transform them into something that is understanding that by the machine learning model that can be understood by the model. So what can be understood by the model? Well, the model only accepts numerical or categorical features. So we really have to transform whatever is our raw data into only numerical and categorical features. So if I take the example of the email, well, we may make a first step. The first step may be to prepare our formatted HTML to transform it into a plain text email, so without any formatting, and by keeping only the content of the email. And then the feature engineering part consists of transforming this plain text into some different features. So it can be the frequencies of some characters like $, exclamation point, things like that. Maybe it's frequencies of some specific keywords like Viagra, buy, email, mail, etc. So these are the features. So these correspond, as we have saw, to column of a data set. And maybe you also want to compute things like the average length of uninterrupted sequence of capital letters, and maybe you can come up with a lot of other features. These are not unique, and generally you will need to improve also and to make an iteration on your feature engineering part to have better and better feature representation and better features that represent your raw data. So we have saw that we need tidy data. What is tidy data? So tidy data is a principle. The idea is that for data to be tidy, we need one example that corresponds to one row, and one row corresponds to one example. So it means that you have a one-to-one correspondence between the example and the row of your data. Also, you have the same one-to-one correspondence that have to exist between columns and features. So it means that you don't have a feature should not be split between columns. And the third principle of tidy data is that you need a single data set. So a single spreadsheet, if you want. You can think of tidy data as a spreadsheet. You have a spreadsheet, and each row you have an example, and in each column you need a feature. You have a feature. So there are different sources of messiness that is not respecting the principle of tidy data. One example can be that column headers are values and not variables name. So it can be the case, for example, if your data are mirrored, if your data is transposed, it means that you have features that are in rows and examples that are in column. It can be the case that way, that you have some values in column header, and it's not a good practice. Also, if you have multiple variables stored in one column, so it can be the case if you have, for example, let's say that you have a temperature, and in one column you have both the value of the temperature and the unit, because maybe it will be you have for some example you will have 20 Fahrenheit degrees, and for some example you will have 20 degrees Celsius. So what you need here, if it's the case, you need a first column that is the value, that is the real value, and another column that corresponds to the unit, for example. Well, the idea here is also that you need to process it to have a single value, a single unit, sorry, if you have that. But the idea also here is that maybe you will have some features that are only accessible to some part of the population, and some other features that are only accessible to some people in the population. But if there are different features, you need to keep them into different and to separate columns and not to merge them. Also, if you have variables, if you have features that are stored both in rows and columns, it's a source of messiness. If you have multiple types of experimental units stored in the same table, well, I already told you about the temperature, but yeah, I guess it's a separate point, but it's also the case. So you need to have a single unit in the feature. And if you have also one type of experimental unit that is stored in multiple tables. Okay, so let's look at one example. So on the example of the left, this is maybe this is raw data that someone gave us. They gave us an Excel spreadsheet, for example, and the data were in that way. So this is not tidy data for different reasons. First of all, you can see that the examples, which correspond to people, are in column. So this is not good, because our value here is what we observe. So we have two treatments, A and B, and we apply some treatment to both people, and sometimes to only one. For one people, we only apply one treatment, and we observe some values. So you can see here that the value that we observe should be in one column, first of all. And here it's split between two rows. So the first thing that we need is to transform this data to have in row, to have one example. And here an example is a person that is associated with a treatment. So for each row, for each row, we put the following column, as you can see, the person, the treatment, and the result. So here, an important thing is that we need one column to correspond to one feature. So here it's the case, in the right hand side, it's the case because the result that we observe is only in one column, the treatment is in one column, and the person is in one column. So if you need more example, if you don't see really what the bad practices mean, I really encourage you to see to read the scientific papers that presented the concept of tidy data, because there is a lot of examples inside, and it's very easy to read. So if you need more examples, feel free to consult and to read this article. It's available freely online, and it's openly, you can access it openly. So the different step of feature engineering is that first you need to define the feature that represent well your examples. So usually you have to involve domain experts from that. So for example, if you are in if you have a machine learning spam filter, you may want to ask some people that some expert in spam, what do they think is a characteristic of spam, thing like that. So sometimes if you work in some specific domain, it will be really useful to work with experts that know what type of feature, what is the characteristic, what are the variables that you can compute that can help the machine to distinguish between what we want to learn. So this is really a good thing to work with experts in the domain that you are working in. Another thing is to document everything that all the features that you have designed. You can do a schema file, so it can be a spreadsheet or a JSON, and for each feature you fill the name, its type. So if it's a categorical or numerical feature, for example, the definition, if it has some missing values, and what does the missing value means, what is the source of the data, etc. So this is really important to document that, because maybe you will not remember later what it corresponds, and it's also useful for domain expert to know what is the features that is using your model. Maybe it will be useful later if you have to work on explainability or to understand what is your model doing. It will be useful to know what correspond each features. So documenting is a really good practice. Then once you know what features you want to use, and you have see that with expert and with other people, you want to implement them. So again, reproducibility and checks. So think that you will need to rerun again the computations, and think about checking it. So you already saw in the first part of the course everything that is unit testing and that is testing software. So keep in mind what you saw that, and this is where you can really use what you learn from software testing in that field, in that part. Also, so what are the different type of computation? Generally, data manipulation can be related to 4 type of manipulation. Filtering, which is selecting only some data. Transforming, which is transforming one column. So you can, for example, transform, if I take the example of the unit, if we have different units of temperature, if we have Fahrenheit and Celsius, well, the first thing to do is to transform the column temperature to have everything in degrees Celsius, for example. Also aggregate. So aggregate is, well, as the name said, is that you aggregate everything. So we will see an example in the next slide. And sort is, well, you know what is sorting. So one useful thing can be to transform the data and to summarize them. So one classical example, and I worked on that when I was a freelance, is churn analysis. So with churn analysis, you have some client and you want to predict whether the client, the customer, will abandon the subscription or will abandon what the company is doing. So here, for example, we have a customer of a mobile phone operator, and we want to predict whether a customer will soon abandon the subscription, because we have some data about previous customers, and we know when old customer quit the subscription. So here we have kind of an issue, because the example is a client. We want to predict whether a client today will, for example, cancel the subscription in the next month. So we have the example is really a client. But if we look at the history of clients, if we look at the purchase that he did, maybe we will probably have a lot of purchase for each client. So the table will be divided. We will have different rows of data for one example. And this is not tidy data. We really need to have one example that we can do. So what we can do is to summarize data. So maybe it makes sense to consider, for example, as a feature, the average amount of purchase that the client did. So maybe the client generally did small purchases, or generally it's in average it's big. Maybe it makes sense also to consider the standard deviation. If you have to summarize data, remember that last week that we have saw the descriptive statistics. Generally, we have said that it's a good idea to compute the mean and the standard deviation, because the mean gives us an idea of the center and the standard deviation gives us an idea of how much is from the distance in average from the mean. So sorry, I mean the average distance from the average. So this is useful, for example, because the standard deviation may allow us to realize if a customer is making always the same purchase in the same amount of purchase the same amount of money, pay the same amount of money, I mean, or if sometimes it's make very small order and sometimes big orders. And if it varies a lot, it will be a different analysis, and maybe the model will be able to use that in some way. So yeah, if you have to summarize data, keep in mind to use the mean and the standard deviation for each features to aggregate. So here in the example, you can see that on the right hand side that we have for each user we have the gender, the age, which are features that are already available at the level of the user. So we already have tidy data. What we aggregated from the three table on the left, which the three table are the table user, the table order, and the table call, is the mean of the order amount, the standard deviation of the order amount, the mean of the call duration, and the standard deviation of the call duration. So you can see that this can be useful. And here in that case, we have the previous order that each user did and the previous calls that each user did. And as we said, each user can do several orders, one or several orders, and can do between 0 and more calls. Okay. So the different steps, the following steps here is to then, once we have do the first two steps, the third one is to encode categorical features. This is really important because we model accept only numerical values, but if you give if you have some categorical feature, you need to encode them into numerical way. So for example, if you have, in the previous example, we saw that we have gender, which was coded as F for female and M for male, but we cannot give directly the character M as a male and the character F as a female to the machine learning model, because the machine learning model only understands numerical values. So what we can do is to encode categorical features into numerical one. So one type of encoding is called one-hot encoder, and this is putting a mapping between, for example, male will be coded as 0 and female will be coded as 1. So we transform it like this. If we have only two possible values. If we have more, we split it into several features. So here, for example, at the diploma, we may have bachelor, master, or high school student, or high school diploma, sorry. So here, what we do is that we have three values, sorry, and we transform it into three features. And you can see that if our first user was a bachelor, then the first row is zero because the first feature corresponds to high school, the second feature corresponds to bachelor, and the third feature corresponds to master. So for the first row, it's 0, 1, 0 because it's not a high school diploma, it's a bachelor diploma, and it's not a master diploma. And then on the second row, it's 0, 0, 1 because we see that it's not a high school, it's not a bachelor, but it's a master. And you encode it that way. One hot encoded means that you put zeros everywhere and one when it corresponds to the good category. An important note here is that you have to be very careful when you encode categorical features, because you don't have to forget it. Because, for example, if you take the day of the week, it will be 0 for Sunday, 1 for Monday, 2 for etc. And you go like this until 6 for Saturday. If you just leave 0, 1, 2, 3, 6, etc. until 6, then, well, if you give that feature to the model will not be able to understand that Sunday is as closely as Monday than it is between Saturday and Sunday. What I mean is that the model will see that you have the biggest gap possible is between 0 and 6. So for the model, if you give just the number of the day of the week to the model will think that the most further apart days are Sunday and Saturday, Saturday and Sunday. So it doesn't make sense. So be very careful about that. And this is something that I saw quite a lot from people that are not experimented, is that they left some categorical feature as numerical one, not encoded in the proper way. So what would be a good way to encode it is to do the same thing as we did, for example, as the bachelor, master, and high school diplomas, is to do some different feature. We do one feature that corresponds to Monday, second feature that corresponds to Sunday, etc. for each day of the week. Okay. This is also valid, for example, as a region number. So if you have a different region, for example, in France, each region have a number, but you cannot give this number directly to the classifier, because it will think that if you give it directly like that, the model will think that there is kind of a continuity between each region, and the region in France are classified, the départements are ordered by the alphabetical order. So there is no geographical sense, there is no sense into considering the region number as a feature. Okay, so what you can do next is to discretize continuous variable. So this is optional, this is not mandatory, but sometimes it can help your model to make some discretization. So what this means is that you have a continuous variable, for example, age, which is a continuous feature. And what you want to do is to create categories from that. So you can, for example, here I created the categories from the people that are less than 18 years old, the category of people that are between 80 years old and 50, and the people that have more than 50 years old. And you can encode it the same way as we saw. This is then you have some discrete value, and you encode it as a categorical feature. So this is optional because you can just give to your model your age, but generally it was shown that in some cases it can help a lot to discretize values, because sometimes the relation may be complex, or maybe you can also incorporate some previous knowledge, because you may know that, for example, less than 80 years old people are minor and they cannot do the same thing that adults can do. So it can make sense to incorporate that kind of knowledge so that the model can learn more easily. The next step that you don't have to forget is to treat missing data. This is really important because some models accept missing data, but most models don't. So you really have to transform missing data. So what you can do? One solution can be, if you have categorical feature, is to give a special category to missing data. So we have shown that, for example, you have the gender, in the gender you have male, female, but maybe you don't know for some people what is a category, and then you can create a third category, which is unknown. Another solution is also called imputation. So in that case, in imputation, you will try to find some method, some heuristic that replace missing values you can replace by the most common thing. So if you have let's say 80% of female, well, maybe you can replace some missing data by females because it's the most dominant character. So sometimes it can be better to use imputation. For example, if you have only very few examples that are missing values and you don't want to remove them, maybe it makes sense to consider imputation because you will not create, you don't want to create a specific category, for example, of unknown gender, for example, if you don't know only one or two gender in the whole data set. So yeah, keep in mind that this is a solution. But the most important thing is don't forget to treat missing data. But generally, model will not be able to learn to train if you have missing data. So generally, you have to manually treat them before. Another important thing to not forget is data normalization of continuous features. So if you have, for example, some continuous features, generally it helps a lot to normalize data. So what normalization of data mean? It can mean that one solution is to remove the mean. So you take minus the mean of each feature, and you divide it by some scale, so that you have a unit variance. So that the standard deviation on the variance is equal to 1 for each feature. So this will help a lot. A lot of model, most of the model will perform better during training if you normalize data, because if you have such a data, the ranges, the scale will be the same between variables, so it will be easier for the model to grasp, to find a meaningful value to estimate its parameter during training phase, because each feature will have the same scale. Because if you have features that take very small value and another that takes crazy big values, well, for some model, for most models, it's really hard to come up with appropriated parameters. So data normalization of continuous features helps a lot. Also, what you can do that is not mandatory, that is optional, is to do some other feature transformation. So, for example, one type of feature transformation is to add polynomial feature. So what does it mean? It means that you put some features to the squared. So you add, so you have, for example, here we have x1 and x2. We have two features. And what we want to do is to add x1, but also x1 squared, and x2, and also x2 squared. And maybe we want also to transform two features. So we want to have x1 multiplied by x2. So this can help in some cases if we expect some interaction between variables. It can help a lot to to do that. So some practical advice here that I really advise you from working in the industry is and also from theory is that first advice is that you need informative features. Informative features means that for the model to be able to learn, the model need high predictive power features. It need basically features that that he will be able to use to train. So if you just give some random features that are generated by randomly flipping a coin, well, the model will not be able to learn anything because if it's not related to the label in the supervised learning case, well, the model will not be able to learn anything because there is no information inside the data. So some people that don't practice machine learning, so some people from business, for example, don't understand that you cannot just give some random data that don't have high predictive power to a model, and yeah, the model is not magical. The idea is that the model is not magical. To learn, it has to be able to access informative features that have signals, that have information. For example, the constant data is useless. So if we take the example of email, well, it's not of email filtering, of spam filtering. It's not useful to put one column that is corresponding to if the email is a spam or if it's if it's an email or not. I mean, if it's always equal to 1, it's not necessary to include this feature. So if you have, for example, in the diploma, if all the people in your dataset have the same diploma, well, it's not useful to add it. So constant features are not useful. Also, totally unrelated features are not useful. I just told you that if you add a feature that is basically con flipping and that is not related to the label, it's not useful it will not be useful to learn. If you have also some duplicated features, it's not useful either. So, for example, if you have the weight in kilogram and the weight in pounds, so there is a direct relation between the two. You just have a coefficient. Well, it's not useful to put the two. Another advice is to always check and think about missing data when you code. So yeah, so once you transform variable, always think what happened if I give a missing data. So I just give you an example, Python example here. So we do a function that is called transform gender here. We give a value here, a singular value here. And if it's equal to male, we'll return 0. And if it's equal to, in the other case, it will return 1. So what's the problem here? Well, think about missing data. If we have missing data that is coming to values, if we have not a number type, for example, well, the gender, the transform feature will be equal to 1. So we will lose the information that the specific gender of this example is missing, and we will categorize it wrongly as a female. So this is not good. So always think of missing data. Also, one advice is to all the data analysis tools that can help you. So think of descriptive statistics. We have so that we can compute the mean, the standard deviation. Also think of the mean, the minimum, the maximum, the quantile, the absolute and relative frequencies, that type of things. Also think that you can use plots, you can use figure, data visualization to help you finding meaningful features, to help you analyzing those features to see if there are some errors, if some features are not useful, etc. Also, you can use some small sample. One useful thing to do is to use small sample to develop and debug. So once you develop your feature engineering, if you work on data that are pretty big, it can take a lot of computation to run. So if you take only some only a small portion of your data, it will be much easier for you to develop and debug at the beginning. But think if you only take that, think also of checking with once you compute it with every data, think of checking well that everything is correct, because maybe you had some specific missing values that you didn't have, or some specific values that you didn't had in your small sample of data. And yeah, you can use unit test for each data extractor, so for each transformation, so each computation of your features. This can be useful. So you may have heard of deep learning. We already saw it on the first video, but as a definition, in deep learning, we have no feature engineering. The idea of deep learning is that it's part of representation learning, and we saw that in representation learning, we don't have the feature engineering part, basically. There is no feature engineering part because we give raw data to the model, and the machine learning model has to learn both the features and how to use it to predict. So this is what deep learning does. And so in deep learning, there is no feature engineering part. So you may think that, well, it's great because feature engineering is really hard, it can be costly, and it takes a lot of time, a lot of computation, so it can be good to do that. But this great advantage came at a big cost. First, you need a crazy amount of example. Generally, you can think of thousands of example or 10 of thousands of example in classical machine learning. With deep learning, we are generally talking of millions. So obviously, it depends on the complexity of your task, because in some more simple tasks, you don't need millions of data. But if we are speaking, for example, of images that are that are not very small, then you need millions of images to be able to learn meaningful representation from deep learning. So it came also as a cost in terms of complexity, because deep learning is much more resource. It consumes a lot more resource when we train and when we predict. So you have to think of that, and also it comes at a cost in terms of complexity to code and things like that. But nowadays that you have a lot of libraries that helps you a lot to code in deep learning, but still it came as a big cost in terms of computation needed. Okay, so this is just a small joke too, is like when to not use deep learning. Well, if you don't be like that guy that just want to use deep learning for the hype of it. And if you have a simple problem, well, you don't need deep learning, and classical machine learning will be enough, and it will save you sometimes. The next step of our journey to the machine learning lifecycle is model building. So model building include choosing choosing a model for your problem, for your task, and also training it. So this is, basically model building is the construction of your model. So here an insight from statistical learning theory from the more theoretical part of machine learning is called the no free lunch theorem. So it means that there is no free lunch. What does it mean? It means that there is no universally best model. It means that there is not a single model that perform good everywhere that perform best for every data distribution, so for every data set. So some model may perform well on spam filtering, some other may perform well on recognizing images of cats and dogs, some other model may perform well on other tasks. So this is quite important to keep in mind because it means that if you have someone that say to you that, oh yeah, you should definitely use this type of model for everything because this is magical, well, this is not really true. Like some type of model works well in some conditions, some other work well on other conditions. And this is proven as a theoretical part. This also means that learning is impossible unless we make some assumption on the underlying distribution of data. So here is just a quick graph don't bother too much, but on understanding it, because the idea is just that if you have a lot variety of distribution of type of data set, and you have different model, well, some model may perform well, very well on some data. So you can see that classifier 2 here, the model number 2, perform really good in the middle type of distribution, so some data set, but perform badly on others. And the classifier number 1, the model number 1, perform generally pretty good, kind of good for everything, but the classifier 2 perform a lot better in the task that he is designed for. So this means that basically you can have a model that perform good enough in all situations, but it also means that some other models are better in this situation. Okay, so some practical advice here is that you can find some empirical guides that can help you. These are not proven by theory, but they are really useful. This, for example, is a flowchart by scikit-learn. Scikit-learn is the main library of classical machine learning in Python. So you can see it. You can pause the video if you want to look at it more closely. But the idea here, if you'd like to take a look at the first node, is that if you have more than 50 examples, well, then you can continue. If you don't, well, you have to get more data because you need at least a minimum amount of data to be able to learn. And then it will ask you if you want to predict a category, if you have labeled data and things like that. So you can see that the different bubble correspond to the different type of task that we have. So you have classification, clustering, regression. You have also dimensional reduction. We didn't see it. It's another type of task, but you can search it online if you're interested. Okay, so this is really useful. I advise you to keep this flowchart and the link in mind and keep it somewhere. And it can be quite useful when you will need it to choose a model in your case. So some other practical advice is to select model with depending on the criterion that you want that you care about. Do you care about explainability? If you do, well, maybe using, for example, a decision tree will be better. If not, you can use some more complex model, some more powerful model. How much example and features do you have? Because some models are better if you have a lot of features and of example. If you have non-linearity of the data, so it means that do you expect that your label will not be linearly correlated with your features? So it means that if you plot if you plot your feature in your label, can you draw a line between the two, or do you think that it will have another shape? So this is a type of, because some model take into account well some the linear dependence of the data, and some other are better are learning nonlinearity. Another question is the computational complexity. How much computation need each model to train? What is the prediction speed? Do you have some requirement on the prediction speed? If you need, for example, the prediction to be computed in milliseconds, or less than milliseconds, it's something that you have to keep in mind because some model can take more time. So you have to choose also a model with best performance, and to evaluate this best performance, you have to use cross-validation. So we will see it in the next slide, but you will understand why I mean by that. But keep in mind that you have to use cross-validation. And also don't forget to tune hyperparameters of your model. We have saw what is an hyperparameter. So for example, we took the depth of the decision tree. If you just take a specific default value of your library of machine learning, well, there is no definitive answer on that. So maybe the default hyperparameter will be good for your task, but probably it will not be optimal. So you can really tune your hyperparameters that way, and that way you use cross-validation, as we will explain later in the following slide, in one of the few following slides, to tune them. So you have different strategy to tune them. You can have grid search, so you put some kind of a grid. So if you have two hyperparameter to tune, you can see it as a grid, and you put each value, for example, to each unit. So you can search, for example, as all the combination. If you have the depth of the tree and another hyperparameter, you find all the possible combination of the values that you allowed it. And also you can have some random search. You can randomly draw some hyperparameter. You train your model, you evaluate the performance, and you see what's the best performance. You have a lot of other strategies that exist to tune your hyperparameters. So let's recall a bit what is the model building strategy. So to build a model, you start with a metric P, a performance metric. So this metric measure how good is your performance of your model. You can make a short list of learning algorithm of model types that you want to use. So you may say that you want to use decision tree, you may want to use a neural network, you may want to use random forest, this kind of thing. Then in 3, you choose hyperparameters tuning strategy. So that's just what I told you. You may want to use grid search. You may want to use random search, things like that. Then you pick a learning algorithm. So you can take a decision tree, for example, neural networks, this kind of thing. And you apply each combination of hyperparameters to the tuning strategy. So you train, for example, a decision tree with the depth of the tree equal to 8. You train your model. So this is the steps 6. Sorry. You use the training set to build the model using the algorithm and the parameters with the hyperparameters value here. So you train your decision tree with a depth of 8, and then you use the validation set. So we will see it in a few slides, but you use a specific training, a specific example as a training, and another part of another set of example, which is called the validation set, to compute the value of your metrics for the model that you have. And then you can decide if my my model good enough or not? And do I have still untested hyperparameters values that I want to test? If it's such a case, well, I pick another combination of hyperparameters values and I train again my model. So maybe I want to try with a depth of 20 my decision tree, and I retrain my decision tree. And if I process again with the step 6 and 7. Once I did that, I can choose what is the best model that I have according to my metric. What is the best metric that I had? What is the so for example, I may see that a depth of 20 is better. I perform better. I have a better accuracy for my decision tree. So I pick this one. I pick 20 as a depth. And then I can try to do the same with other type of models. So maybe I want to try with random forest, and I can tune the hyperparameters of random forest. And when I'm done with random forest, I can try with hyperparameters of neural network and things like that. And when I'm done tuning the hyperparameters of the model, I can compare the model to see which model performed best, which is the best metric between models. Okay, so hopefully you understood the model building. It was a big, an important step. But what you want to do now is to evaluate your model, how my model is performing. So to do that, recall that we have overfitting. So be careful with overfitting, because remember that with overfitting, that we had with our algorithm, we're kind of learning by heart the examples that we give him without learning the true signal, without learning the true pattern that we want him to learn. So in that case, to have a good idea of the metrics that we choose, what is the good performance of our model, we use cross-validation. So to use cross-validation, what we do is that we shuffle the examples. So so that there is no pattern. The ordering of example doesn't influence the way that we will estimate the performance of our model. We shuffle them. And then we split it into 3 distinct sets. So this has to be distinct. So it means that each example is either in the first one, the second one, or the first one. No examples should be both in the training set, the validation set, and the test set. So this is also why we said at the beginning that it's important to remove duplicates in the data. It's because once you split your model into the 3 distinct sets, you don't want a duplicated example to be in both sets, because it will you will not have a good estimate of your model. So this is a good estimate of your performance. So the first set is the training set. So the training set is, as its name speak, it's for model training. So this is the example that the model will see when it learns. The second one is called the validation set. This one is used for tuning hyperparameters and for choosing the model according to the strategy that we just saw. So this is important to have a third set, which is called the test set, to have an independent evaluation of the final model. Because think of the case where we have a lot of hyperparameters and a lot of hyperparameters values that are possible. As we combine them, maybe we will train thousands and thousands of models. And in that case, well, you can see that maybe you have some, it will when we train it, if we try a lot, thousands and thousands of model, well, maybe one will perform better than another one, but by pure chance. It's just because we trained so many models that maybe one will perform a lot better, and we'll kind of see the same pattern, is that if we allow so many models to be trained on the same data, well, then it will kind of we will overfit to this data just by pure chance. It's like basically you toss a coin, and if you keep only the face that you want, one of the two sides of the coin, well, in the end, it's not generated by random if you just select the ones that work well. So what you want to do is use this third set, the test set, to have an independent evaluation of your data, because you don't want you want a separate set of example to have an estimation of the performances, and this is for your model, for you to be able to understand what performance you can expect from data that were never saw by your model. So this is kind of representative of what happened when we will deploy our model. Because when we will deploy our model will perform kind of the same way as the test set, in the sense that it's example that the model never saw. So one good practice also here is to split into these three distinct sets before at the beginning of the training, before the data preparation, at the beginning of the pipeline. Why? Because sometimes we will see it later, but sometimes we have what we call data leakage. Is that we will have some information that come from the training set that will go into the test set. And if we have such data leakage, well, then you see that the whole purpose of the test set is to have an independent evaluation. If we have some leakage of information from the test sets that go into the test set, then our evaluation will not be independent. It will, if we overfit to the training set, then we will overfit to the test set, and the evaluation of the performance on the test set will not be representative at what will happen when we will deploy our model. Okay, so one thing also is to choose an appropriate metric for your problem. This is important in the sense that sometimes some metric will measure, as we saw at the beginning, some acceptable and unacceptable behavior. This is important to choose a metric that represents well what you want. So you report it. The final one that you want to report to, for example, to your boss or to the people that will use it, is the one computed on the test set, because this is the independent evaluation. So if you report to some accuracy, for example, you only report the one on the test set, because this is the final one. And the people that don't practice machine learning, that don't care about training the model and everything, only cares about the final accuracy. And you can compare it with you can compare your metric with a baseline. So what is a baseline is basically, well, I say it's a point of comparison. What can be a point of comparison? It can be the performance of the simplest algorithm that you think. So it can be, for example, random labeling. So what happened if you randomly label emails between spam and not spam? And does your algorithm perform better than this? So for example, let's say that we have the same amount of emails that are spam and the same amount of emails that are not spam. Well, then the baseline of accuracy is 50%. Like it's the most simple thing that we do. If your model is performing, if you have an accuracy of 50% in that case, well, your model is useless, because it's not doesn't do better than just randomly drawing a label without having any information. So it's basically useless. A baseline too can be also human performance. If you have some tasks, how the human perform. So the human can perform very well. So if a human have to distinguish between cats and dogs, generally, so maybe it will not be equal to 100% because in some cases you can be wrong, but it's generally very easy to perform such a task. But for other tasks, it may be really hard to have it. So, for example, if you have to classify some X-ray scan, it may be really hard to come up with a decision. Also, something to be careful here is what is called class imbalance. So, class imbalance is a problem when you have not the same amount of example in one class and in the other. So consider, for example, credit card fraud detection. So you have some transactions that are made from credit card, and you want to detect fraud. So hopefully you don't have the same amount of fraud than you have the same amount of real transaction. And what you can expect generally is like kind of 1%, for example, of fraud among all transactions. So here, imagine that you choose to report the accuracy. What is the baseline in that case for accuracy? Well, the baseline is 99% of the time, because if you just classify every transaction as not a fraud, then you have 99% of accuracy. So if you achieve 99% of accuracy, it seems to be exceptionally good. It seems to be really great. But when you think about that, if that's the simplest algorithm, which is just nothing is a fraud, then you have 99% of accuracy. So this shows that the accuracy in that case is not relevant. It's not allowing us to distinguish well. We need some other accuracy. So for example, specificity and recall that we saw. And also it's important to keep in mind the baseline. So also remember that we have saw the detecting underfitting and overfitting. So I will go quickly and I will send you with the second video. In the second video, we covered what is underfitting, overfitting, which is oversimplification of the data for underfitting, and overfitting is fitting the noise to the data. So you can detect it by comparing the error, the average error that is computed in the training set or in the test set or in the validation set. So generally we prefer the one in the test set, but if you are tuning your hyperparameters, for example, you can use the one in the validation test and comparing with the training test. So this is useful. Why? Because it can allow you to choose more wisely hyperparameters, or you can choose more wisely the model that you want to tune. Because if you are in the case of overfitting, well, it means that your model is too complex. So maybe if you have a decision tree that is 1,000 depth, well, it's a crazy lot. And maybe it's too complex and you are kind of remembering all the example and you are overfitting to the example and you are not learning the true data, the true pattern. So maybe you want to tune your parameter in a different way and things like that. Also, if you are underfitting, it means that maybe you need to have you probably need to have a model that is more complex that allow you to tune better your data. I mean, to tune better your hyperparameters or to change your model. One important thing in model evaluation is to be aware of data leakage. So I already talked to you about that. You have really to be very careful about data leakage because if it happens, it means that the evaluation of your metric is bad. And also it means that when you will deploy your model in the production, when it will be deployed, it will not perform as you expected. And it can be really bad in some cases. So, for example, data leakage can happen if your example are not independent, let's say. So you have some examples that were gathered at different time, and maybe they will influence each other. So it can be the case, for example, into malware detection. If you have malware and you want to predict if you have software, sorry, and you want to predict if it's a malware or not. Well, generally, people in malware develop some framework and use some techniques that are similar to each other. And you have kind of like the first malware that use a technique, and the other maybe will copy it, or maybe the malware author will publish some framework to allow and to sell to other malware author for them to write malware. So you can have some information that come from each other, because you have basically some malware that copies each other. So this is an example of data leakage. And if you can think of kind of duplication. If you have the same malware components that is in the test set and that is in the training set, well, maybe your training data, your test set, sorry, will not be a good representation of what will happen if you deployed it, because maybe all the techniques change and you have new techniques that are still unknown by your model. So it may not be a good evaluation of how your model will perform in the future. So this is the general overview of data leakage, is that you have information that are not available at the prediction time, that is contaminating the information available at prediction time. So this can be also some images that are very similar to each other, for example, or things like that. It can also be, in some case, that you have some features that are, once you train your data, that are available. So if we take the prediction, the prediction of house pricing, well, maybe in the data you didn't really look at it, and it's bad because you have to look at what data you have and what features you have. But maybe one of the feature is, for example, how much the person from the housing agency, took. So if you have the agency fee, well, generally it's a proportion of the price of the house. So if you have this example in your data set, well, it will be, you can perform, your model will probably perform really good, because the model just have to learn that he has to multiply the fee of the agency by some amount, by, for example, 10, if the fee is 10%, and then he can recover magically the price of the house. But obviously, this is contamination, because you have some data that are not available at the time of prediction, because when we want to predict a house, the price of the house, obviously we don't know the agency fee that is associated to it. So this is, keep in mind, data leakage is really something to keep in mind, and in all the process, in all the machine learning pipeline, you have to ask you, am I leaking data? One thing that you can see here in the machine learning lifecycle is also that there are some arrows that point from the model evaluation to the feature engineering, to the data collection and preparation, and to the goal definition. So these are, you can call it feedback loop. So you evaluate your model, and once you evaluate it, you may see that you need, for example, to have more data. So you go back to feature engineering and you had some data. So it can be that, for example, you have a really bad accuracy, and you see that the features that you thought of, that you designed, were not didn't have enough information, didn't have enough power of to predict your label. So you go back to the feature engineering part, you add more feature engineering, and then you continue the pipeline, you build your model, and you evaluate it, and then you see if it has improved your performance. You can also go back to the data collection or preparation if you see that you have some bad data, if you see that you have some that your model is performing bad because you have data that is expired, that is not relevant anymore. You can go back to this preparation step and remove some of them, for example. You can also go back to the goal definition if your model is not performing good enough, or if you need to rethink the task that you are doing, things like that. You may need to go back from the beginning and to change some specific point. So the idea here is that we kind of have a loop that is kind of never ended. So because we can always go back to previous step to improve our model. So this is an important point, is that the model design is never end if we don't set goal. But this is not necessarily a problem, because we can deploy a model that is good enough and then continue to work on the designing of model to improve models. Okay, so let's go back to the general picture. So what we did is that we saw that we start from a problem, we write down every aspect of the goal, every aspect of the task, the different elements that we saw, and then we go to the data collection preparation step. We prepare and we clean the data. Then we compute our features that we then feed into the model. In the model building part, we tune hyperparameters, and we train models, we choose them, and then we evaluate the model, the built model, the trained model, on an unbiased, another separate data set to enable to have an unbiased estimate of the performance. So here we saw the phase of designing model. But keep in mind, something important here is that your job does not end when we go to the model deployment, because once your model is deployed, you can see that from the model maintenance, you can go back to feature engineering or go back to data collection and then continue the loop. Why? Because, well, sometimes the data set that you gathered will be different from the one that will be fed once you deployed it. So you can think, for example, if you do image classification, maybe in your data set, you only have a beautiful picture and perfect pictures that were taken by a professional camera and really good camera. But maybe what your user will do is that they will take photo with their phone that have in low light, that are photos that are blurry, that have not the same quality and the same properties as the one that you have trained your model on. So the idea here is that it's really important to monitor the performances of your model once you're deployed it, to be able to learn if there are any problems and if you need to do some model maintenance, and then go back to the designing a new machine learning model. So the idea here, in conclusion, what I want to emphasize is we build a model, but once we build it and we deployed it, don't forget that your job is not finished. Because what generally people said, and this is an important step for software engineers like you, is that if you do some in machine learning engineering, the model fails silently. So generally when you know that better than me, but once you build software, if the software failed, well, the application crash. We have bug reports, and it failed with a big boom. It doesn't fail silently, but for machine learning, it does. If our model is slowly, if the performances of our model is slowly degrading for some reason, well, then if we didn't deploy actively some model monitoring to check regularly the evolution of the performances, we have no clue that our machine model is performing bad. So keep in mind, once you have deployed it, that machine learning model fails silently. Okay, so here a list of some links that can be useful for you. In Wikipedia, there is a list of data sets, so it can be useful if you are wondering what are the different type of tasks, what are the available data sets that you can do to play with it. The documentation of scikit-learn, which is the main Python library of classical machine learning, you can start with that. You have also a cheat sheet of scikit-learn, so it's better to take a look at the documentation and to be a bit familiar with scikit-learn, and then you can use that to quickly recover what you will learn. And also, if you are interested and you don't have so much time to read a 1,000-page book, you can see the 100 pages machine learning book from the same authors on machine learning engineering, and you will have in a concise way you will have the different aspects of machine learning. Okay, so these are the references of the course. So you have a machine learning engineering book. So this is not published yet, but the draft is available there. I took quite a lot of contents there and I reviewed it. It's a really good book. Also, you have Machine Learning, a Probabilistic Perspective. This is a really big book. It's more than 1,000 big pages of content, but this is a good book if you want to go into more detail. You have also the part on statistical learning theory. We are taken from this scientific article, and you have also the scientific article called Tidy Data that you can look if you want more information about tidy data and more example. Okay, so I want to thank you all for following this class. I hope that you will be fine. If you have questions, feel free to ask them in the forum part dedicated to machine learning and statistics on Moodle. And also, if you have the answer to some question, please answer to the other students. Okay, so I hope that you enjoy the course. Good luck with the other part, and yeah, I wish you the best.